Much, good morning. I'd like to welcome you to the first plenary sessions of our META'15 conference and thank the organizer for organizing this great upcoming conference in the city. It's my pleasure to introduce two of our distinguished colleagues who give the plenary talks in this first session. Professor Clarke Gmachl from Princeton University and Professor Vlad Shalaev from Purdue University. Claire is going to talk to us about the quantum cascade lasers and applications in mid-infrared photonics. Please join me in welcoming Claire.
All right, thank you for the introduction, and I would like to thank the organizers for inviting me here. I want to thank them for their vision and their courage to invite a topic that is quite broader or a little bit far off of what the core topics of META conference are. So I'm going to be talking about mid-infrared quantum cascade lasers and their applications. And it's a very, very broad topic that ranges from material science to applications like sensing applications, and that topic is too broad for 30 minutes, so I'm going to pick subtopics that touch on the fields of the META conference, and wherever I can I will throw out challenges where these topics need applications from plasmonics, need applications from photonic crystals, need your ingenuity to help solve some of the problems that we encounter in our research. I was really happy to be here at City College because several of my dearest collaborators on material science, Maria Tamargo, Professor Dong Shen, and in applications, Barry Gross, Fred Moshari, are actually here at City College. So it's a wonderful place to be here. Driving in this morning in the thunderstorm was an extra treat. So thank you again for the invitation and for bringing me here. So I want to talk about quantum cascade lasers and applications, and before getting into the actual topic, let me thank my student groups, a dedicated group of graduate student postdocs, several of whose work I'm going to be showing actually have moved on to postdocs and industry positions. And this is my summer group, so this is my graduate students plus some of the summer students this summer, because it's really them who do much of the work, most of the work that I'll be showing you today. So when I'm talking mid-infrared, I'm using the term very loosely, anything from wavelengths of 3 microns all the way out to 30 microns. And it's a wavelength range that interests us for many good reasons. I think one of them is it's the wavelength range where molecules have very strong fundamental resonance. It's the rotational vibrational resonances that are in that wavelength range, such as the ammonia molecule, something that's intrinsically hard to measure because it's so sticky. It's a very sticky molecule, so trying to measure it by itself is very hard, and light is a good way of measuring it. And it has this fundamental vibrational resonances in the mid-infrared range. So we're working with some of the strongest light-matter interactions that there are if we look at molecular chemical sensing using mid-infrared light. Another good reason is that's the wavelength range of heat. And so up there's some folks playing with their own thermal imaging. So it's a field of imaging, a field of night vision, a field of energy, right? Knowing where we lose energy, knowing where we can recover energy. So it's a field of energy recovery. When we talk about sensing, it's a field of environmental sensing. So it touches on fields that are important to our everyday lives. It's also a field where semiconductors can very easily be manipulated to display a very wide range of dielectric constants just by doping. And semiconductor people know how to dope semiconductors. So by going from undoped, you're basically looking at that dielectric with refractive indices around 3-ish, 3 to 4. But if you dope them, you end up basically in the metallic range. And you can do anything in between at layer thicknesses that are much smaller than the wavelength, and you can keep layering them to total thicknesses that are well above the wavelength range. So in terms of designing materials, building materials, where you have control over the dielectric constant in a very fine way, this is a very opportune wavelength range and a very good material system to work with. Furthermore, not on this slide, if you wanted to go quantum, you can do that too. So you can go with quantum wells and you can throw in some energy resonances, so that's an added benefit of working in the mid-infrared and in quantum wells. So I hope I motivated some of the reasons we are in the mid-infrared wavelength range, why we work with semiconductors, semiconductor layers, and we dope them. And it's the same toolbox that I know is part of your toolbox, of the toolbox of the META community, designing materials, designing abilities into materials. It can be passive materials, for waveguides, splitters, whatever what you want to do. It can be detectors, and we work with City College on detectors a lot, but it can also be active devices such as lasers and emitters. And so let me go a little bit closer into that part of the field, which is quantum cascade lasers. And in order to make a laser, we need to get population inversion between upper energy level and the lower energy level. We have to pump energy, population, into an upper energy level, and then empty the lower energy level below, so we get population inversion between the two. And if we can get an electron stream with an electrically pumped device, we're going to get a laser. That's a very, very, very quick way of saying it. So what you're seeing here is the conduction band energy of a multi-quantum well structure. So every box here is basically a single quantum well. We mostly work with indium gallium arsenide quantum wells, aluminum indium arsenide barriers, and indium phosphide, just because they're so convenient to grow. What makes it a laser? Electrons scatter, electrons move, they tunnel or scatter into an upper energy level, and that's where they are. They can't really move on. They will make a scattering transition to a lower energy level, especially if it's empty. And we want it to be an optical transition. And if we get an excess of optical transitions, we can put it into a laser cavity, get some optical feedback, we can make it a laser. How do we usually engineer these lasers? Well, we think about optical phonons, lattice vibrations, as the strongest scattering mechanism in the system. And so we calculate the optical dipole matrix element that gives us the strength of the optical transition. We also calculate the optical phonon transitions. So how fast is the non-radiative scattering, and the non-radiative scattering out of here. We engineer this, we'll make laser out of it, and ultimately the lasers end up being very decent lasers. So we'll put in current at a certain voltage, and then we'll get light out. Here's a threshold, a very decent, very strong threshold, and then power levels somewhere in the watt range for a good laser. So that's, in short, conventional quantum cascade lasers. I can show them also what they physically look like. They are little strips of semiconductor etched out of a wafer. If we keep zooming into here, we'll see those layer structures. And if electrons move through the structure, every time they hit what's called an active region, they will emit light. If we keep zooming in, into closer and closer, what we recognize is that these layers aren't perfect. They aren't smooth. There's quite some roughness into that system. And recently, that's been growing in importance, the actual physical makeup of the layer, of the structure on the atomic scale, recognizing that this will have impact on the actual performance. And so if we look at roughness, at that interface roughness, it actually can cause scattering between subbands as well. So an electron can go from an upper level to a lower level in the quantum well, not just radiative, that's what we want, not just by optical phonon scattering, which we know will happen, which we'll exploit for population inversion, but also by non-radiative scattering. And it can be very fast. And so including that now into our new designs, we can make better lasers. And everyone, I think the whole community starts including more and more scattering mechanisms into the design of the lasers. And so a good laser would look about like this, rather than having a single upper level, because they dephase so quickly and they scatter so quickly, states blur into each other. So we can actually use a whole band, a continuum of states, to broaden the starting energy of the transition. And then we'll have the landing energy levels where the electrons will transition to, and again we're going to take a continuum. And so we're going to get electron optical transitions from like 1 to here, and then from higher states to a couple of states. So we're going to actually get a continuum transition to get a certain breadth into the transition. And this is an example of a really good laser. Output power levels in the watt range, even at room temperature, efficiencies in a couple 10% ranges, and not too demanding in terms of the power requirements in terms of current and voltage. And because it starts from a certain width of transition, ends at a certain width of transition, it actually has quite some spectral range, which then can be used to build spectrometers. This would be in an external cavity, a laser tunable across a very wide wavelength range. And this type of lasers has entered the commercial realm. This is just a list of companies we work with and we're familiar with, or are sort of somehow related to our engineering research center on mid-infrared technologies for health and environments. But you get commercial suppliers of a good number of these devices already. So then the question is, well, if you can buy them, what kind of research do you want to invest in? What are you going to do? And I showed you the power levels on an earlier slide. The power is good. For most applications, let's talk sensing, let's talk imaging. What you really need is a couple of milliwatts, 10 milliwatts, maybe 100 milliwatts. And you can fairly straightforwardly pull them up to watt of powers. So power, check, you're good. How about the spectral width? If you want to replace entrenched technology, which is big boxes that you have to drive around in trucks in order to, let's say, do sensing in an urban environment, since we are in an urban environment. If you want to replace this entrenched technology, you have to at least match its abilities. And one of the beauty is broadbandness. So let's look at how can we make our mid-infrared technology even more broadband. And so here's an idea why, well, you ask, okay, what keeps it from being really broadband? And the answer is, well, a classical quantum cascade laser has an electron stream from an injector into an upper laser level, which could be a couple levels, into a lower level, and then that's the classical cascade scheme. And the width of the transition is then given by the width of the starting and the landing energy levels. And that gives you a decent tunability already. But what if you could take your stream of electrons that you inject through the contacts and divide it up into not just one cascade, but multiple cascades? You can take some of your electrons and siphon them off and put them into another cascade, in another cascade that has other optical transitions. And then sometimes they might rejoin and then split up again. And so that's the design of it. The requirement is that the length of one period would be very short, so that electrons can actually zip through and past a single stage in order to enter excited levels in a downstream region. So the conventional quantum cascade laser is going down here, going down here, going down here. But we populate higher states and then have so many more energy levels to play with. And indeed, that will give you a very broad electroluminescence, just to get emission, just to get, okay, the range over which I can get optical emission, can get optical transition in this particular structure is actually 3 to 12 micron. And the 12 micron cutoff is because our detectors cut off there. So we actually expect from theory, from modeling, that we have room out in that range. And then just a free running laser itself. Just if you turn it on and let it run by itself, see where it wants to lace, sometimes with a little power, sometimes with a lot of power. Even that range is from 6 to 12 micron. And then you can force it with some means, making a distributed feedback laser, probably by making a photonic crystal out of it, to lace at whatever wavelength you would like it to. So now I put a little check mark next to broadbandness. So at the beginning I said I want to look at both the field of metamaterials, plasmonics, and see where there are connections to the field of quantum cascade lasers and applications. I think one example where I see a great overlap is how well the field of metamaterials integrated theory, real, serious, solid-state theory and modeling with experiment, and how beneficial that is. And that's not something that the mid-infrared intersubband field really is. We did a lot of experiments first, theory second. But sometimes that's not the best way of doing it, and here's an example for that. Alex Song was doing a lot of this work, and so his job was, let's look at intersubband transitions in gallium nitride or aluminum gallium nitride. And why would you want to do that? Well, that material system will provide you with a band offset that's much larger, and so you can go to much shorter wavelengths. Let's go beyond the 3 micron short wavelength cutoff to the 1-point-something micron regime. And doing that, it works. You can make intersubband transitions and you can measure them. But there's a consistent discrepancy between what you calculate, which says, well, this is my energy, and this is the scattering. And even the scattering, if you count the scattering of phonon scattering, that will be the width of your transition, and that will be the energy position of your transition. And it's a consistent discrepancy. The system yields, you make your quantum well wider, your energies are smaller, your transitions are smaller. You squeeze the quantum well, energies go up. So it is a system that follows your expectations, but it's quantitatively off. And with that, designs that are more complicated, like detectors or emitters, fail. Right? So Alex was, he's a genius. So he started looking at the actual system, not looking at the quantum well as a quantum well with roughness added in phenomenologically as a broadening, but he really had to look locally because these are very thin wells with a fairly large roughness. So this is pretty much to scale, at least in the vertical direction. And so he put this all in and calculated the actual potential, the actual transition followed then. So instead of having this quantum well potential with the inbuilt fields that are unique to gallium nitride, aluminum gallium nitride, you end up with a new potential that is much less deep and also doesn't have all these peaks over it. And immediately, having these transitions, it made the calculation fit the experiment well. There's a little bit of a fit parameter in there, which is the roughness, and you can match that up with roughness measurements from AFM, which fits very well. Just to see how theory and experiment need to go together to really get you the deep understanding and that enable you to do things. And so what does it enable you to do? Well, before we knew to rescale and remodel our potential, we were not able to get an emitter. Just any attempt of getting emission would fail. Intercept-band emission would fail. But once we had the new model with the new potential, this is electroluminescence from gallium nitride intercept-band transitions. And the detectors work too. All right. In intercept-band transitions, because there is so much non-radiative scattering, you get very little spontaneous emission out. Lasing is different. You know? The optical transition, once your laser light is on, becomes very fast. The transition becomes the dominant scattering mechanisms. Then you can put energy into the optical field as much as you like. But before threshold, when the optical field, the density of the optical field is very low inside your device, spontaneous emission, you know, is very rare. Maybe 1 electron out of 10,000 or less will make an optical transition because of the non-radiative scattering. So usually intercept-band emitters are very poor spontaneous emitters. Lasers, great, but spontaneous emitters, no. But sometimes you do not want a laser. For example, if you think about imaging, if you want to use light for imaging, a long coherence length is only a hindrance because it, you know, throws your speckle everywhere and you kind of lose the depth information if you use light that has a kilometer coherence length. So we were looking for something that has short coherence length and high power. That would be an optimal source for what's called optical coherence tomography, where you send in light into a material, it bounces off hidden surfaces, hidden interfaces between different refractive indices, real and imaginary indices. And it bounces back and you can reconstruct the inner workings, the inner structural information of the system. But to do this, you need short coherence length, that gives you the actual depth resolution, and you need power, because otherwise your light gets absorbed and you won't get anything back. Right, so how do you make it not a laser, but get power? And the answer is superluminescent structure. That's what it's called. It's a superluminescent. It's just before lasing. You get the benefit of amplified spontaneous emission, you get the benefit of amplification, of gain, but without the actual laser gain. So here's the challenge that I promised you, right? We want as much amplification as we can, but don't let it go above threshold, okay? So how do you get a laser not to go above threshold? Poor mirrors. Very poor mirrors, very low reflectivity mirrors. And sort of one embodiment of this, which told us we're kind of on the right path, is a rounded back facet that's etched. And the front is a cleaved facet, but at 17 degrees, because we need one place where we actually get light out very well. This thing scatters light into the substrate or someplace else. While it's a poor mirror, we can't collect light from this one. So here we need this facet to collect light. And it gives us a milliwatt of output power. And we can get a decent beam coming from it as well. A milliwatt's okay, but we need better. So how do you get more power? Well, if you run through the whole theory of it, you need as long a cavity as possible. Makes sense, right? You get a lot of amplification if you go for a long distance. And you need very poor reflectivity, very low reflectivity. Okay. If a chip is very large, it's sensitive to breaking. So in order to get a long cavity, we had to go away from the linear cavity idea and basically go to a curled up cavity. So the next cavities were curled up things with a rounded edged back facet and the front 17-degree cleave. And these things go 30 milliwatts of power for an 8 millimeter, 12 millimeter, 60 milliwatts of power. We need more. We want more. You think about imaging sort of things on your skin, or art conservation, if you want to see oil paintings underneath other oil paintings, you know, what the artists have hidden or painted over. You don't want to destroy it. You want to have IR light go in, bounce back off the different layers, and come back out. Right, so the trick is you want to turn, this is all pulsed, so the average power is not very high. So you want to, this is luminescent, superluminescent power, and then eventually it hits threshold. So as long as you can keep it from going above threshold, you're good. So we had to change the reflectivity even lower. So we now, what we're using right now is actually when you, so this is the pumped spiral, eventually curls into a loop which is not pumped. So it has the absorption of the regular waveguide, and we played around with different types of loops with metal or without metal in order to get the reflectivity down. And so now we are at 100 milliwatts of output power, which is already very good, but it's limited by, okay, let's do 100 milliwatts of output power, coherence length in the order of 80, 90, 100 micrometers, which is given sort of also by the spectral depth of it, which is good for a lot of structural investigations. What are we limited by is the reflectivity of the mirrors. If we back out the reflectivity that we have here, we are talking about somewhere in the 10 to the minus 5, which is 10 to minus 4, 10 to minus 5 regime, which is actually very good. So anti-reflection coatings don't really work for us so well. First of all, getting them to that number is very hard. And secondly, they wear off over time too. So we need the front mirror, which is very transmissive, which gives us a lot of power, a lot of light throughput in a nice beam, again with very low reflectivity. And the back mirror, we don't care where the light goes, but very low reflectivity. So if you can pull this down, we would get even more power out of. And we can curl it to longer length. So that would be great benefit. What do you do with it? Well, you build that system. You build that optical coherence tomography system that gives you that imaging capability for your structure. And so the way it works is you have your source. It sends your light pulse into your sample. At every interface, at every place where refractive index changes in some way, you get a little reflection. You overlap that reflected light with a copy of your original beam, which you split off and you measure. And you get an interferogram. And then you just calculate it, you transfer it back to your real structure. That's how OCT works. But because we're working in the mid-infrared range, where materials absorb so strongly, this is a little bit like a Fourier transform infrared spectrometer as well. You're not only getting structural information, you're also getting chemical information. So if you get a feedback from two of these bounce backs, you can actually look at the light coming back in that time interval. You do a Fourier transform, you get the chemical information as well. So you get non-invasive, non-destructive, three-dimensional imaging with chemical information, as long as you have enough power to actually penetrate to those layers to get the light back out. And so we built one. It's kind of the first such system, not counting the systems that use lasers, which don't have a depth information. So we built the system, and we just look at layered mid-infrared materials right now, and for every surface you actually indeed get a bounce back. And lately we put some chemical, some non-transparent, some partly absorbing materials into the cavity, and indeed we see the spectral information as well. So what's the challenge here? Well, first it's the mirrors. And the second challenge you kind of start already seeing here is this is all still big optics, because most of it we're using light traveling in free space. So if there is an opportunity to miniaturize, to capture the light, to transport this on chip, would be a great benefit as well. So, up to now, I hope I told you a little bit about mid-infrared inter-subband devices, starting from material science and how important it is to really take a thorough, deep, solid-state physics kind of look at the materials you're working with. But then it enables you to do a lot, like make awesome lasers and emitters. And I didn't show you detectors and nonlinear structures, but there's so much you can do by engineering your transitions, your quantum levels, but also your dielectric constants, if you want. What are applications? I'll just show you two very, very quick ones. One is, I'm going to start it out with, it's environmental sensing. Here's some slides from a colleague of mine, Professor Zondlo at Princeton, and his group. Sensors have become, so mobile that they get strapped onto cars. Somewhere is a laser, somewhere is a detector, and the light bounces in open air. And so as it's driven through the countryside, as it's driven through places, it can measure a whole lot of chemicals. And so the classical chemicals environmental scientists will be looking for is carbon monoxide, ammonia, methane, and these kind of things. And so this is just driving this car around Princeton area. So if you follow a truck, if you're behind a truck, emissions go up. If you drive into an animal farm, this is chickens, the ammonia level will go up. So it's a very fine tool to pinpoint very closely pollution sources and then aggregate them. So I've been driving around Princeton, around Houston, around Beijing, around Pennsylvania, a little bit west from here is a large, it's called the Marcellus Shale, where a lot of the shallow oil wells are, or natural gas wells are for fracking. So if you drive downwind past one of these fracking sites, you actually measure a whole lot of methane leakage. There are trucks, or actually small trucks driving through New York City, trying to sniff out leaks of natural gas that come from the natural gas pipelines that fuel this city. So there's a lot of good stuff you can do with this technology. Or medical applications. We look at it to measure glucose in human skin. So the laser will shine onto the skin. If it hits the depth where interstitial fluid is, which also has glucose in it, it will bounce off whatever fibers are in the skin and come back out in a very rough scattering pattern. So you can't predict which way your light is scattering back out. Can come any angle, plus minus 60 degrees in all directions. But if we capture that light and we analyze it, we can actually get glucose concentrations that's very similar as those measured by the finger prick. So these are actually, depending on how you process it, if you have calibration spectra or not, you can actually get clinical accuracy or better. What's the challenge here? Well, right now we're using an integrating sphere to collect the light. Because the laser shines on, this is daylight solutions, tunable laser shines on the skin, we use something around the arm or the hand, and the light can come back out of the skin in any direction. So right now we're using an integrating sphere to collect the light onto the detector. Knowing that it comes at a huge angle range, is there something that you can build that has this large numerical aperture but will get that light to the detector very efficiently, very quickly, without the losses that are usually counted in a sphere? So that's another challenge. And then the next challenge is to get these systems, which are actually already fairly compact. This is the laser, this is the detector, this is the sphere, this is just a hole in the sphere where you put your hand, into something that's even smaller, miniaturized. Can we get, the laser is a small chip, the detector is a small chip. Can we get everything else onto a small chip? So let me conclude with thanking all the people who collaborated and worked on these topics, and together with collaborators that do much of the growth, but also put in their smarts and their theory and funding from the National Science Foundation. And thank you for listening. Thank you.
This requirement you mentioned for the very low reflectivity that you need, over what bandwidth? Is it you need to have it that low reflectivity over the entire band of your system? And
the question is, we need low reflectivity mirrors, and yes, we do need them over the entire bandwidth of our gain material, because as soon as it lasers, it lasers.
Let's thank Clarke one more time. Thank you very much. The next plenary talk will be given by Professor Vlad Chalayev from Purdue University on